So we had some tricky complex numbers problems that we've been working on, and I wanted to just demonstrate a couple of them. The big idea in this unit is that you want to just be fluent at switching between Cartesian form and polar form and using that RE to the I theta idea to make things easier on yourself. So, for example, one question asks us to consider what happens when we have a complex number to the n plus its reciprocal. And so what I do is I think of that in terms of the RE to the I theta. And the question asks us actually a simpler version where the R value is equal to 1. If the R value is not equal to 1, you don't get quite as interesting of a result. So what we are assuming here is that the R value is equal to 1, and that implies that my Z is just e to the I theta. In other words, cosine theta plus I sine theta. So let's write it in that form. E to the I theta to the nth power plus 1 over e to the I theta to the nth power. Using my exponent properties, I know that's the ni theta plus negative ni theta because it's on the bottom of the fraction. And I remember that cosine theta plus I sine theta is the same as e to the I theta. So when I see e to the ni theta, I can write that as cosine of n theta plus I sine of n theta. And then the negative powers are written almost the same, like this. Now there's something that you really should know about cosine and sine. You can either do it by looking at their graphs or by thinking about the unit circle. If you rotate theta, an angle of theta, in the counterclockwise direction, in the positive direction, and you rotate the same angle in the clockwise direction, the two x values are the same. In other words, the cosine of a positive angle is the same as the cosine of a negative angle. But the two y values are opposites, so that means that the sine of a positive angle is the opposite of the sine of a negative angle. And applying those two ideas, I can see that this piece is identical to this piece, but this piece is the opposite of that piece. So I end up with 2 cosine of n theta. We have this wonderful identity here. Please keep in mind this identity only works when the r value is equal to 1. Think about why it would break down. If the r value was not equal to 1, then I'll just write it in purple. I'd have an r right here and an r right here. I'd have an r to the n here and a 1 over r to the n here. You can't do anything with that. But when the r value is equal to 1, then we do have this beautiful identity. So now what we're asked to do is to try to play around with that. So let's look at, for example, if we had just z plus 1 over z to the fourth power. Using the binomial theorem, I know that this becomes z to the fourth plus 4z cubed 1 over z plus 6z squared 1 over z squared plus 4z 1 over z to the third plus 1 over z to the fourth. You can just work out, Pascal's triangle down to the row going 1, 4, 6, 4, 1. But I'm going to use my identity, and I notice that this left side has an n value of equal to 1. And I notice on the right side, I've got an n value of 4. And here I've got an n value of 2 because they cancel each other out in a nice way. So I'm going to use this 3 different times. So the left side of the equation becomes 2 cosine of theta to the fourth power. The right side becomes 2 cosine of 4 theta because that was from my n equals 4. And then plus 8 cosine of 2 theta. That was my n equals 2, but I have a coefficient of 4, plus 6. And so using this idea and multiplying 2 to the 4th and cosine to the 4th, I'm able to come up with cosine of the 4th theta, and 2 to the 4th is 16, so I'm going to just go 1/16 to slide it over to the right side of the equation, and I come up with this wonderful little identity. And the nice thing about this identity is this is true for any angle. And so this is something you could use if you were trying to do some sort of a crazy integral or something like that. And so if I wanted to integrate, for example, cosine to the 4th theta d theta, I could integrate just the other side instead, and then each of the cosines turns into sine, and you just have to divide by the coefficient of theta. So if I wanted to do the antiderivative here, I just get 1/16. Let's see if I can fit it in here. 2 over 4 sine of 4 theta plus 8 over 2 sine of 2 theta plus 6 theta plus c. And then we've got that right there. If we had bounds of integration to plug in, we plug those in, we get a nice result. This is a nice technique because there's no u substitution, there's no integration by parts that works. So it's only by resorting to using complex numbers that you'd be able to solve that sort of an integral. So that's kind of sneaky, that's kind of tricky. Let me know if there's anything I can do to help.